Good morning. I am Gijo Raj. I'm a scientist at the Sree Chitra Tirunal Institute for Medical Science and Technology in India. Today, I shall present this work on supramolecular organization of model polycyclic aromatic molecules, comparison of 2D and 3D assemblies. And this work was done during my research associateship at New York University in Abu Dhabi under Professor Hans Naumo. And in this work, we collaborated with our colleagues from National Institute of Advanced Industrial Science and Technology, AIST in Japan, where we did this STM work under Professor Yoshihiro Kikawa and Professor Yasuo Norikane. So, in UAE, petroleum is a major source of revenue, and petroleum extraction involves a lot of challenges. The most important challenges is the deposition and plugging of asphaltenes in oil pipelines. So asphaltenes in the oil industry are known as cholesterol of the oil industry. In UAE alone, around 100 oil wells are affected by this asphaltene plugging. About $3 million per year is spent about for 35 cleaning operations per year. And these cleaning operations are limited by equipment. So the strategy most widely used is to use what is called inhibitor molecules. These are chemicals specifically designed to prevent asphaltene deposition and thus build up and plugging of this oil well. For example, in the figure, you can see an oil field engineer close to a pipeline that has been plugged with asphaltene deposits. And one such incident occurs, and that can happen very quickly actually. And once it happens, it's extremely difficult to make these cleaning operations, and it ends up usually in the closing or shutting down of the oil well, and then a lot of investment is needed for cleaning up operations. So constant monitoring of conditions to prevent this asphaltene deposition is one of the major activities in this petroleum extractions. And asphaltenes, chemically, they are defined as heavy fractions appearing in the crude oil. These are class of polycyclic aromatic compounds that are defined by the solubility, and that is, they are soluble in toluene and they are non-soluble in N-heptane or linear alkanes. So during oil is formed over millions of years ago, years under equilibrium conditions, very down under the earth, under these oil-forming rocks. Then what happens one day? We try to drill this oil out. So this oil, from its stable conditions of temperature and pressure over millions of years, suddenly encounters these abrupt changes of pressure and temperature, and these conditions actually trigger the stabilized asphaltic molecules to aggregate each other and then form asphaltic aggregates and final depositions, and that happens very quickly and plugging the whole oil well. So chemically, there are different, since they are a mix of thousands of compounds, and their basic structure is that they have a polycyclic core, that is fused aromatic rings with appended side alkyl chains, and also it have what is called heteroatoms. These are atoms like sulfur, oxygen, nitrogen present in this aromatic core structure. The two famous models of asphaltenes exist. One is called the island model, where these asphaltenes have a central aromatic core with appended alkyl side chains. Then they have what is called the archipelago model, which is where you have these alkyl, the aromatic cores are connected by alkyl chains, as we can see. So since these asphaltene molecules are extremely difficult to isolate, fundamental studies in order to understand their interactions are mostly performed on asphaltene mimicking materials. So these are like model compounds, and one such compound is what is called this violentron, which have almost these 9 fused rings on its aromatic core, and then they have these appended alkyl side chains, as you can see here. And this is the heteroatom, the oxygen, which is colored in the red. This is the heteroatom, the oxygen. So this is a model molecule of asphaltenes. So in this study, so why it is important? It's important to understand how these molecules, when they are depositing on surface, how these supramolecular, these supramolecules arrange on the surface. Why it is important? Because depending on this arrangement, their properties can differ. For example, when these asphaltenes are deposited on mica, and then when these asphaltenes are deposited on HOPG, the AFM force curves or the adhesion characteristics are different. For example, this is an AFM image of how to say asphaltene deposit that you can see, which are formed on mica, and this AFM tip is brought into these asphaltene deposit on mica and perform this force distance curves. And the deposits on mica, these force curves, this retraction curves here is represented in the red color, shows different steps or peaks, different steps showing different adhesion events. Well, however, when the same molecule, asphaltenes, when deposited on highly oriented pyrologic graphite, and force measurements on these deposits never showed these adhesion steps, meaning their conformations are different on both these substrates. Another indication is the height measurements of these deposits. They are very larger. They are larger in the case of deposits on mica when compared to the deposit height on HOPG. So in the HOPG, this forms a more compact structure. The molecules try to have a flattened conformation, have a better interaction with the substrate. While on the mica, we know it's hydrophilic, and these hydrophobic chains of these molecules tends to form this sort of a coil structure or some sort of an agglomerate. And this particular differences in the conformation surfaces have a drastic influence on the nature of the adhesion properties of these materials as well as its viscoelastic properties. Most of the oil bearing rocks are made of sandstone or which have calcium or limestone reservoirs. In the UAE and the Gulf region, these are mostly limestone reservoirs. And limestone reservoirs mostly consist of calcite minerals. They are formed of calcium minerals. So here is an example of how when asphaltenes looks like when we deposit onto a calcite crystal surface. So this is a topography of a freshly cut calcite crystal, and where you can see there is a steps, and these steps are 4 angstroms or about 5 angstroms in step. And so these are single mono layers of calcite crystals or the calcite molecules forming these crystal steps. So on the right hand, the image, we see the topography and phase contrast image of asphaltenes deposited on this calcite surface. And what we can see in the phase contrast, the asphaltenes appear as darker when compared to these bright calcite regions. So another thing to notice is these dark deposits are continuously forming across the interface or the valley or the crystal edges, as you can see here. So here is the same image showing that, the same image of a freshly cut calcite crystal. So there are different crystal planes, different steps. So asphaltenes preferentially prefers to adhere along these steps. We can see that, and in height image it is not much evident, but in phase contrast image allows us to see this with a better contrast because phase contrast is depending upon the viscoelastic properties of the crystal and the deposits, which is asphaltene. So asphaltenes are more viscoelastic or like more soft material when compared to the hard calcite crystal, and this difference in the hardness or the stiffness directly influence the phase lag when the tip is tapping onto these different materials. So that's why we get this phase contrast, or more energy is dissipated in the soft asphaltene deposit. But nonetheless, beautiful thing is that we can see these deposit with a very clearly distinguish these two different materials. So it's so from these examples of asphaltene deposits on different substrates, and depending upon the nature of the substrate, it forms different conformations, and depending on these conformations to the substrate, it influences its different natures like or properties, physical properties like adhesion, stiffness, or preferential orientation to deposit across the surfaces. So the objective of this work was to investigate a supramolecular organization of model asphaltene molecules, which is called violent trend 79, adsorbed onto a solid liquid interface. So we wanted to see, because asphaltenes are complex mixtures of molecules, so we can't isolate a single asphaltene molecule. This is extremely difficult and has been not easily performed. So the idea is to take a similar asphaltene similar molecule and try to see how it deposits or get absorbed on a single molecule level onto the solid liquid interface. And the technique that we use here is the scanning tunneling microscope technique, where we have a conducting tip which is in the form of a platinum iridium wire that is being cut, and our sample is this highly oriented pyrolytic graphite, which is an excellent surface for STM imaging. And then we solubilize our violent molecules in what is called the 1-phenyl octane medium. And 1-phenyl octane is a substance that is kind of neutral, electrically neutral. It doesn't conduct. So this is a safe solvent. So we can put this asphaltenes and we deposit this violent dissolved in the 1-phenyl octane and deposit on the HOPG. And when that happens, the asphaltene molecules in the 1-phenyl octane deposit starts absorbing to the surface, starts absorbing to the highly oriented pyrolytic graphite. And depending on the interactions of the molecules with the substrates, it can form certain organization on the surface. And our objective is to use this STM technique to observe in a molecular scale this arrangement of molecules or the primary molecules that absorb onto the surface. So the principle of STM is that when this metal tip is and the sample, and we apply a bias voltage between them, and when the tip is sufficiently close to the substrate, what is happening is what is called a tunneling phenomena. And the tunneling phenomena is the crossing of these electrons from the tip to the sample at very short distances. When the tip and the samples are extremely small, under the applied voltage, electrons tunnel between the extreme end atom of the tip to the sample. And since this tunneling takes place between the atomically sharp or between the end atom of the tip to the sample, this is the reason of getting the molecular level resolution for this kind of image. And normal AFM tips will never get this level of resolution. So since this tunneling occurring at the extreme between the extreme atom of the tip and the sample, the spatial resolution is by far highly enhanced. We can reach atomic level resolution. We can see arrangement of atoms on surfaces. We can see arrangement of molecules on surfaces. And why this tunneling takes place? Because tunneling takes place because it's also an example of the wave nature of electrons. So in the wave nature of electrons, when the barrier here, when the electron hits like a barrier and the barrier thickness is large, it will not penetrate this barrier or tunnel this barrier. But when the barrier thickness is smaller, getting smaller, the electron, due to the wave nature of this electron, the electron easily tunnel across, and this barrier thickness is the range of a few nanometers, or even the thickness of one molecule. So here is an example of the STM image of violent molecules deposited at the HOPG 1-phenyl octane interface. Here is a 100 by 100 micrometer image where we can see a patterned surface occurring, and a closer look, 50 into 50 nanometer zoom image shows several ring-like structures organized across the surface. So here is the tunneling parameters that we observe used for this image, which is the V bias, which is the bias voltage between the tip and the sample. Then another parameter is the set point current. So that means here is 3 picoampere. So set point current is actually according to the principle, when the tip is, we will set when the tip is coming closer and closer to the surface, so extremely close, where this tunneling happens. When the tunneling happens, a current is measured, and we can set this value of current. This is called the set point current value. So if we increase the set point current value, that means let's say 10 amperes. So what happens is the sample is moving closer to the tip, so that more electrons are tunneled, and so more current is reached. So this is the principle of this set point current. So if the set point current is less, that means that we will lower the sample so that that low value of current is only measured. If the set point is 0, that means there is no tunneling, it's very far apart. So we play with the set point current value as well as the bias voltage between the tip and the sample in order to control the resolution of these molecules, to observe these molecules on the surface. So this is the two important parameters that we control in the STM technique to get molecular level resolution of the samples. Here is a further zoom, an experimental zoom of these ring patterns, and we can see that it forms a lattice arrangement, a 2D arrangement on the surface. And when we can do molecular modeling using a software of these violent molecules, and when we could even superimpose these molecular models across these features observed, and we can see that these nano rings that are formed are composed of arrangement of about 6 individual violent molecules on the surface, as depicted in this figure D here. And in order to go to further, zoom onto this finer imaging or high, molecular level resolutions, we still play a little bit with the bias voltage and the set point current. So here are the lattice parameters of these 2D arranged structures. This A and B are, the unit cell parameters, which is 3.68 nanometer in the A and B. And the gamma is the angle between this A and B, which is 64 degree. And this work was recently published. Here is the reference for that. So when violentron or this polycyclic model compound adsorbed onto the HOPG 1-phenyl octane interface, it forms this nice 2D arrangement of nano rings. So here is another, we wanted to show the repeatability of this process. We checked with different substrates, with different tips, and and we ensure that what we are seeing is not artifact but real thing. So here is an example of an extremely large area in terms of STM size, about 200 to 200 nanometer size. We can see it's forming across the surface. It forms uniformly. And another interesting parameter that we noted is, these rings, the diameter of this inside ring, this L, is actually twice the length of this the alkyls, the C8 alkyl chain of these molecules, as we can see here. So we see how these molecules arrange in 2D. It's also important to see how they arranged in 3D. Because in AFM, this is something important also, because we would like to verify the structures we observe with AFM with an independent complementary techniques. So here you use the TEM, transmission electron microscope. This is directly performed on a bulk, on a small piece of a bulk crystal of this violentron. So this violentron crystal was sonicated in water actually. So it was sonicated, and because we don't want to dissolve it, we wanted to observe on the bulk thing. So this was fragmented to very fine pieces, and then we focused onto a very a very flat, very thin, atomically thin slice of this crystal, and then we see this high resolution TM image, and we can see that repeated structures, periodically arranged structures forming across here, and this is a cross section, and we see there have very periodic arrangement of molecules there, and this and with the long range order, and these domains here, what we see as fingers, and these domains are separated by around 3.6 angstrom as well. So this 3.6 angstrom is very close to what we see in the lattice parameter that we observed in the STM image. So in order to understand what are these, why this, to understand the real arrangement in the bulk, we did what is called the 3D structure analysis of these crystal molecules with single X-ray diffraction. In the single X-ray diffraction analysis, the violentron is actually forming what is called this helical conformation, helical structure, where the primary interaction is between the aromatic centers, the aromatic cores. This, as you can see, this green and the orange aromatic core, that forms a distance of about 3.7 angstroms due to the pi-pi interactions. So in the bulk, these pi-pi interactions are governing the arrangement, and the periodic structures that are separated by 3.7 angstroms in the 10 image is actually the pi-pi core that we are seeing. On the other hand, in the violentron case, in the 2D imaging of in the STM, the interaction here is guided by the epitaxial interactions of the alkyl chains of this violentron to the orientation of the carbon atoms in the HOPG surface. So this is what it is in the figure D. The arrow here, the arrow in the top bottom is representing the orientation of carbon, the epitaxial arrangement of carbon atoms on the surface. So as you can see that the nano rings, the violentron chains, the alkyl chains of violentron molecules in the nano ring are aligned to the epitaxially arranged carbon atoms in the HOPG in every directions. So in the case of the 2D arrangement of violentron on the surface, the epitaxial interaction of alkyl chains are highly playing a very important role in driving these molecules for forming these supramolecular assemblies. While on the other hand, in the bulk crystal, there is arrangement, long range arrangement, and that is governed mainly by the pi-pi interactions between the aromatic centers of these polycyclic aromatic molecules. So this is the interesting comparison that we, and in XRE, actually, we still get this lattice parameters. Actually, we will get a true 3D lattice parameter for the A, B, C, and components. And the A and B are 3 nanometers, while C is 1.84 nanometers. So actually, this forms a tetragonal system. And a slight differences, because these are very close to what we observe the A, B parameters in the STM image, and these are very closely related. And slight discrepancy is probably due to the conditions of how these measurements are performed, or the conditions these measurements performs, because In XRD, the measurements takes place at 100 Kelvin, while in AFM, this is at ambient conditions. So there is this thermal differences, but still on the goal, these are very, very good indications. And what we see, very good correlations between 2D arrangement or the lattice parameters of 2D arrangement with the 3D in the bulk crystal. Extremely interesting. So in conclusion, the lattice parameter of 2D unit cell of violentron adsorbed at HOPG 1 Finlaught interface are on the same order as that determined from the bulk crystal through XRE and the TM measurements. On the surface, the assemblies of the molecule is mostly driven by epitaxial interaction of one of the alkyl chains of this violentron with HOPG, and also self-association, because these heteroatoms can form hydrogen interaction with the neighboring molecules. So self-association and epitaxial interactions forms these 2D patterns. Here is the example of that. However, in the 3D, the interactions are mostly governed by the pi-pi interactions that forms this helical structure. So the goal, the insights on how these molecules are arranging on surfaces and what are the forces that play these arrangements are very important. In terms of practical applications, such clues will help us to design better inhibitor molecules whose primary objective is to prevent this asphaltene adsorption onto the surface or deposition on the surface and remain in solution, for example. To prevent this asphaltene adsorption, because the first step in asphaltene deposition is adsorption. And if an inhibitor molecule can prevent that, then we can get rid of this plugging or the blocking that happening in the pipelines. So that is the story. Thank you very much for your kind attention. And I also acknowledge New York University in Abu Dhabi to fund this research, and the ADNOC company for this research, and the support from ACE in Japan is deeply acknowledged. And thank you very much for your kind attention.